I'm Alex Beret, and this is Lab 3 Constant Velocity Motion. I'm in Lab Section MO5, and I observed a rolling $1 coin on a table, and I applied the momentum principle and Newton's second law to the model when the net force equals 0 because the velocity is constant to predict motion. Here's my video. I used the Xbox in the background as the calibration stick, which was 0.3 meters. And I set the origin and grid lines to indicate that the left is the positive X direction. And as the coin rolled along, I set the center mass as the average position. The time between each clip of the video was about 1/30th of a second, and the total time for the video was 1.3 seconds. The mass of the coin is 0.001672 kilograms. And to find the average velocity, I took the final position minus the initial position and divided it by the total time, which I gathered the final and initial positions from the tracker video and calculated the average velocity to be 0.613 meters per second. The time step I used, 0.034, was also taken from the video as to what time increments it used. The module corresponds to the time of the video, and I used Newton's second law to define the new velocity using this equation, which means that the final velocity must be equal to the initial velocity. So F net divided by the mass times delta t must equal 0, and if delta t is always increasing and the mass is 0.001672, then F net must equal 0. So this is the run of the module. The ball moves to the right, which is indicated as the positive X direction, and the graph begins at the origin and moves in the positive X direction. This is indicated by my graph. This is the plot of the model and the experiment. The model is in blue and the experiment is in red. The wave in the experiment line is because of the trajectory of the coin as it was rolling along the table. And for the most part, the model follows along pretty closely with the experiment, or with the observation, so the experiment was successful. The answer to the question, what if the axes were switched to denote the ball going in the negative X direction instead of the positive X direction? Negative X would now be to the left. So that is indicated right here, changing the initial position to be negative and the initial velocity to also be negative. And a run of this module also indicates that the ball moves to the left and the graph goes in the negative direction. The answer to the question, what does it mean that the net force is equal to 0? Well, since the velocity is constant, the net force must be 0, thus the pushes and pulls must also equal 0. If the net force was not equal to 0, then the velocity would not be constant, which is indicated in this module. The net force, there's a slight net force in this module, and a run of it indicates that since there is a net force, the velocity is constantly increasing as time increases, and it is also illustrated by the graph.